Hey gang, good to see you again. As always, welcome back. We've had a pretty heavy last few lectures, heavy in theory anyway, so this one's going to be a little bit lighter. Just kind of go over some concepts to wrap up our exploration of the introduction to geometry on the ellipsoid, and then just touch on geocentric coordinates on the ellipsoid. First off, I would like to introduce you to the NGS toolkit. The NGS puts out or posts on their website a series of tools, quite a few tools, lots, hundreds of tools, to help you with navigating some of these geodetic calculations that we're doing, a way for you to check your work. So I'm going to show you one today that will calculate for you from geodetic coordinates, latitude, longitude, height, to XYZ coordinates, the geocentric coordinates, and then back again. This way, it just gives you another way to check your work. You can go on to NGS and type in your results and see if they actually work. So NGS toolkit. What we're going to do and I literally went to Google Earth and just zeroed in on Flagstaff, Arizona, and kind of got the centroid of it and got the geodetic coordinates. So the Flagstaff, Arizona, the center-ish of Flagstaff, Arizona, we have a latitude, elliptical latitude, or a geodetic latitude of 35 degrees, 11 minutes, and 12 seconds, north latitude. And then lambda, the longitude, is 111 degrees and 39 minutes and 23, 23 seconds. And that's west longitude. And it gives it an elevation of 7,001 feet. I want to say a word about elevations. We haven't started talking about the different types of elevations that we need to use in our calculations yet, but we have, there's many different types of elevation, hundreds. In general, however, we really only are concerned with either orthometric height, which is a height that's perpendicular to the geoid of the Earth, an equipotential geodetics or gravitational surface. We also have ellipsoid height, which is the elevation above our theoretical ellipsoid, whether it be GRS 80, Clark 1866, or others. So the 7,001 feet is any elevation you get off of a USGS quadrangle or Google Earth or any map is representative of an ortho height, and the orthometric height being in reference to a geoid. NGS toolkit asks for an ellipsoid height, but we're just going to use the ortho height and pretend like it's an ellipsoid height, because there's a lot more steps in getting the geoid separation and calculating that ellipsoid height. It's not difficult. It's easy information to find. It's just a simple subtraction or addition, but we haven't looked at that yet. So just for ease of demonstration, we're going to use the ortho height and pretend like it's an ellipsoid height, because that's what NGS would like. If you go to Google, and I have Google all all keyed up and ready to go. Queued up is what I meant to say. And if you just type in NGS Toolkit, there it is, and just click on the first option. Here is the toolkit that some of the tools that NGS offers. And if you look down in the bottom section on the right, you see XYZ coordinate conversion. If you click on that, then you have two options. You can go from latitude, longitude, height, I'm down at the bottom here, to XYZ, or the other way, XYZ to latitude, longitude, and height. So since we got our latitude and longitude from Google Earth, let's do that one first. And we have a latitude of, and it tells you how to enter the latitudinal coordinates. So we have, that's a north latitude of 35, 11, 12 north. And a little word of caution, because is that if you have a single digit minute or degree or second, you have to put in trailing zeros, because the software that NGS uses recognizes the number of digits. So for example, if it was 35:01 or 1 minute 12 seconds, then you'd have to put N350112. So account for those zeros, the placeholders. So that's our north longitude, and we have that's our north latitude. We have a longitude of 111.3923, and that's a west longitude, which from the example we have to put in the beginning. So west longitude, and our ellipsoid height, quote unquote, that we're using is 7,001 feet. So we have all that in there, we submit it, and we get this report. Oh, we get an invalid report. Why did that happen? I didn't enter. Oh, you have to put a decimal in the 4 seconds. So it'd be 12.0 and 23.0 seconds and 7,001.0 feet. There we go, and submit. And there we go, we have it. There's your XYZ on the GRS 80 ellipsoid. So your geocentric coordinates on the GRS 80 ellipsoid, right there. And you can write those down. And just for kicks, let's go the other way. So I'm going to go back. So now we're going to take those XYZ coordinates we just calculated, plug them in, and see if we get those same results back. So we had an x of negative 192, 1927, 951.5594, and that's a negative. Negatives are important. And our y value is negative 4855482.9105, and hopefully I'm not fat fingering anything so I get these weird results. And then our z value is 3658845.8062, and we submit that, and lo and behold, we get the same coordinates back. The latitude that we had, the longitude, and the ellipsoid height, quote unquote ellipsoid height. So this should be pretty valuable for you when you're calculating coordinates that we will be doing. And now you have a way to check if your results make sense or not. Okay, so NGS Toolkit, really valuable. And I'll get rid of that. Don't need that anymore. And I'm going to erase this stuff rather than just moving it up, because we don't need it anymore. And I want to wrap up our initial exploration of the ellipsoid geometry just by making a couple observations for you. So on a sphere, let's see. On a sphere, we learned that the shortest distance between two points is along the great circle. Okay, so if you remember, we defined the great circle on a sphere as a plane that intersects the sphere and contains the center of that sphere. Now, when we talk about the great circle between 2 points, that plane is going to include those 2 points and the center of the sphere. So obviously, a great circle curve is a planar curve, a 2D curve, right? So if we have 2 points here and a center of our curve, or the center of the sphere, we then have 2 radii that are equal, right? Ugh, it's so light. So that's a straight line, if you couldn't tell. And here, darken that up. Again, straight line. And then we have the curve between them, the great circle curve. So this curve is a 2-dimensional curve, and our radii are the same. And remember, on a sphere, the radius of our curves are also normal to the curve itself, so perpendicular to the tangent to the curve at those points. And this is so the great circle curve, the curve is a 2D curve. That is, we can represent it on a piece of paper, we can draw it. The bullet point, the radii are equal. And that's not true on the ellipsoid, is it? We don't have equal normals, either our radius of curvature or our geodetic latitude line, our normal in the prime our normal vector in the prime vertical. Those are not equal at each point; they're different. So let me make some more room. I don't need little messages. Okay. There, I'll leave that. So on the ellipsoid, however, in general, the normal vectors to 2 points are not equal. Also, they are what's called askew, meaning that those normal vectors do not lie on the same plane. And that kind of works. I'll just use some pencils here. So say we have one line. So say that's a normal vector. We might have another normal vector that is askew. That is, you can't represent them on the plane. They're not parallel. They're not intersecting. They're askew. So non-planar. And as a result, we're going to look at the shortest distance between 2 points on an ellipsoid. But as a result of the normal vectors not being planar, that curve that results from the shortest distance between 2 points on an ellipsoid, that curve is also not planar. To visualize what a non-planar curve looks like, imagine having a spiral, a segment of a spiral, and if we stretch it out, far enough, it's going to be a line, right? But if we leave it as a curve and look at it, there's no way that spiral can be adequately represented on a plane. There is no plane that contains a spiral. The same is true of the shortest distance on an ellipsoid. It is non-planar. So what does it look like if it's not planar? We know that. Okay, let's see. So on the sphere, the shortest distance is along the great circle, and it's planar, a planar curve. On the ellipsoid, if we have 2 points, the shortest distance between them is sort of this wavy line like that, which is really weird. And it's also non-planar. So it's a non-planar curve. And of course you're asking the question, well, why don't we use a great circle on the ellipsoid also to represent the shortest distance? Well, for one thing, there is no planar curve on the ellipsoid that would represent the shortest distance. And for another thing, great, I lost what I was going to say, but for another thing, we haven't defined a great circle on the ellipsoid, have we? We could say, if we were to intersect an ellipsoid with a plane such that the plane contains the center of the ellipsoid, that could be called a great ellipse, I guess, if we were going to extend our definition of great circle. But it's not really something that is used or defined in this context. So we haven't defined it. So this curve has a name, and it's a pretty easy name to remember. It's called a geodesic curve, or just a geodesic. And we often say geodesic to mean the curve itself. So I'm saying a lot today, aren't I? Apologies. So let's see. On ellipsoids, elloids, I'm just going to leave it like that. The shortest distance between any 2 points is called a geodesic, and the geodesic is a 3D curve that does not lie on a plane. And let's see, I'm just going to put here in parentheses, think of a subset of a spiral. All right, so that's the definition of that. I also want to point out real quickly We also learned that on a sphere, new idea, on a sphere, again, so again, I'm just wrapping up with a few conceptual topics. Let's see. We learned that following a static azimuth, that is, we're not accounting for convergence, we're just following a one azimuth, results in a loxodrome, or that's also sometimes called a rhumb line, RHUMB line. So loxodrome or a rhumb line. And if I'm looking top down at the sphere, so here's the pole, and we're in this ship, and we want to go from this point to this point, and we put in an azimuth. We find that we're actually going to miss that point, and we're going to begin to spiral around the pole. And if we were infinitely small, we would never actually reach the pole. We would just spiral forever. Now, what is a great circle distance of 2 points look like in this context? Well, say I want to go from this point on the loxodrome to this point, but let's say I am adjusting for the azimuth. We're going to follow something closer to a great circle, and that's going to look more like a straight line between the 2 points. A little bit of curve to it, but it's a great circle curve. So that's interesting to know. So the loxodrome, fun stuff. Little bit of geometry fun. So let's go on to the next idea. Let's see, I'm going to pull in an image here. Let me find it. Where's my images? There's my images. Let's first look at a lateral view of the spherical model of the Earth. Lateral view. And I'm going to bigify that so that it's easy to visualize. There we go. So this is a lateral view. Let's label our parts. It helps us with... Here we have the equator. Up here we have the pole. And we learned that if we have this point that's up on a mountain maybe, that we have a radius to that point, right? And we call that r plus h. It's the radius of the sphere plus our little height above or even below the surface of the mathematical model of the sphere. And we called our latitude psi. Let's see. If we were to drop a project our point down to the surface of the equator, which is the xy plane, right? So that's our point projected onto the xy plane. So that's a right angle. We found that this value, we defined this as z, with this being our z-axis, the spin axis of the Earth. And we derived that z equals r plus h times the sine of the latitude. geocentric latitude. That was one. And then with the, scoot that aside and bring over a top view. And bigify that one. So here's the top view of the spherical model of the Earth. This is how we came up with our geocentric coordinates. Don't want to lose my Z. There we go. So in a top view, we have the pole. I'll write it down here. That's the pole. And then we may have a point on our latitude of interest here. Let's see, what am I missing? We have our x-axis, our y-axis. Then we can, I'm going to move that point over to a line of longitude. So we have our longitude. And then we have our line along the meridian to that point. And if we dropped use different color. If we dropped a projection line down to the x-axis and did the same thing on the y-axis, so then this is our x. Let's give this point name. Let's call our point Q. So that would be x sub Q, and this line would be y sub Q. We have our lambda. That's the longitude of our point, right? We found that we derived that x equals r plus h. I really should have these memorized, but I don't. Cosine, I'm going to try to do it from memory. Cosine of psi, cosine of lambda. Whoop. Right? And then y, our y coordinate is equal to, oh yeah, I'm not looking. I didn't look, I promise. R plus h cosine of psi sine of lambda. And we have that. And we found that those weren't too difficult to work with, right? So this is top view. So the question now is, what is our what is the ellipsoid equivalent? So how do we find geocentric coordinates on the ellipsoid? This I'm not going to draw out because I don't need to. It's actually really simple. I'm just going to move this over here so we still have our spherical, and get that off here. Sometimes it takes a while to move these things around. And I'm going to erase all the other stuff there. So this is on the sphere. Now it begs the question, what about the equivalent on the ellipsoid? It turns out it's not that much different. On the ellipsoid, we just replace r with our normal vector in the prime vertical, our radius of curvature in the prime vertical, which we called n. I'm going to put in parentheses mostly. The z coordinate is just a little bit different, and it makes sense why it's different when you see what it is. So on the ellipsoid, we have x equals n plus h times the cosine of phi times the sine of phi. Make sure I'm getting that right. Yep. And y equals n plus h times the cosine of the latitude times the, oh, I made a mistake. That's supposed to be cosine. And if this were a live class, you would all be yelling at me right now because that's all burned into our brain. And then y is the cosine of the latitude, n plus h times the cosine of the latitude times the sine of lambda. Boy, I really screwed up that x value. You're all saying, geez, get it together, Rob. Okay, lambda. So those are the values. That's our x, that's our y, and z is almost the same as on the spherical case, but we have to scale it. So it's actually n times 1 plus epsilon squared, where epsilon is derived from our a and b, our semi-minor, semi-major axes, and then plus h. Notice it's not n plus h times the sine of the quantity of 1 plus epsilon squared. It's n times that quantity plus h. Make sure you take notes correctly, times the sine of the latitude. And that's it. Pretty simple to find ellipsoidal coordinates given latitude, longitude, and then our height, our elevation. Remember, the n just comes from the definition of the ellipsoid, so that's pretty easy. Okay, so coordinates. There's still one category of coordinates that we haven't talked about at all. And it happens to be the coordinate system that we're most used to working as cartographers and surveyors. Let's see. So we've talked about geocentric coordinates, or XYZ. And the LGH coordinates, or latitude, longitude, and height. Or in some cases, lat long. You'll also see it represented as lat, long, and r plus h as part of the coordinate. So we've talked about those on both the sphere and the ellipsoid. There's one more, and it's called, oh, sorry, that's not LGH, it's LBH. A lot of mistakes today. It must have been a hard day. LBH. So what we haven't talked about is the third type, which is LGH, which is what I wrote before. I kind of spoiled the surprise. So LGH, which is the ENU, or northing, easting, and up. Or easting, northing, and up. And we certainly know what northings and eastings are. We know about latitudes and departure in regards to the LGH coordinate system. And like the geocentric coordinates, these are linear coordinates, so they'd be in meters or international feet. And you'll see people still working in US survey feet, but it's been deprecated, so I'm not even going to write that down. So LGH coordinates are dependent or derived from upon some projection. And a couple of bullet points about northing, easting, and up. I'm running out of space. I'll go up this way. So some LGH facts. The origin may be any point. So we're no longer interested in the center of the sphere or the center of the ellipse or the spin axes. We're going to actually move to some new axes, and the origin of those axes can be any point whatsoever on the sphere. So coordinate axes are, as we said, the easting, northing, and up. These are Cartesian coordinates. I didn't have that written down, but I think it's important to point out they're Cartesian coordinates. And we're going to work with them as Cartesian coordinates, just like x, y, and z. Let's see. What is the up axis? If up is an axis, what is it? So the up axis is coincident or collinear with the ellipsoid normal. So that's that vector of curvature, or that radius of curvature. And since it's an axis, it doesn't matter if we're talking about the radius of curvature in the prime vertical or just the regular radius of curvature. It could be n or m, because axes, remember, we're only concerned about direction and the metrics that we're using. So let's see, the n-axis is coincident with the meridian of the origin I'm going to have to move up. I'm running out of space. Oh, shoot, I'll just have to erase that. That's not erasing. There. So that leaves us with the easting axis. The easting axis is perpendicular to the n-axis and contains the origin. What that kind of looks like, I didn't really think I was going to draw it out, but I think I will. Where is my ellipsoid? There's my ellipsoid. I lost it. There we go. So what does that look like? Remember how I said it's dependent upon a projection? Well, a projection is going to eventually end up as a plane. I'm going to use that color. So let's say our origin is here. Just in general, our origin is right there on the ellipsoid. And we have our plane, and the origin is the point that is on both the representative plane as well as the ellipsoid. And at that point, our northing axis would be along the, I didn't draw that very well, but it would be along the meridian. So it'd be more like 3D drawing is hard. So the meridian here would be like that, right? Because the meridians converge, and then the easting axis would be perpendicular to that. And the z-axis, I'm going to have to draw differently. Let's say that here's my developable surface or my plane, and the origin touches it there. Or I said z-axis. I meant the up-axis would be along the ellipsoid normal. So it's that's the up-axis. And that makes sense, because if you're standing on any point on the ellipsoid and you look directly up, it's with a line of gravity, and that's the up-axis. It just contains the origin. So the LGH coordinate system, we're not going to get real deep into it right now. We're going to, that's what's going to be coming up next in lectures, is we're going to start deriving the NGS or the LGH coordinate system. One more thing I wanted to touch on today's lecture is, remember that we have covered two types of latitude. And if you remember way back in when I introduced types of latitude, I said there were three we were going to talk about. There's a lot of different kinds of latitude. We're going to talk basically about the three. We've talked about the two types, which are geocentric latitude, psi, and phi, which is geodetic latitude. And then we have another one. It's called beta. We use Latin letter or Greek letter beta, and that's called the reduced latitude. And it's a little weird. I will try to draw this out. I think what I'll do is I will I'll just zoom in. I'm just going to zoom in on a quadrant so I can draw this a little more effectively. So if I zoom in on a quadrant, So there's the northeast quadrant on my ellipsoid, or quadrant 1. And how am I going to draw this? So first of all, we have a point. Say, I'm just going to put it right on the ellipsoid. We'll call it point Q. Let's draw what we know. If we draw the normal vector at Q along the radius of curvature, what do we call that? Well, that's our geodetic latitude, phi. And if we draw a vector from the center of the sphere to Q, then that we called psi, geocentric latitude. So what is beta? Once you have that, I'm going to, so this is our normal vector, n, or m, because remember they are parallel and coincident. It's just the n extends to the spin axis. So I'll extend my n. That would be n. If I shorten it, that's m. So we've gone over that ad nauseum. What would be the beta, or the reduced latitude? If I have my point, before I talk about the latitude, I need to introduce the concept of auxiliary sphere. And there could be a lot of different auxiliary spheres. It just means a sphere that has a radius equivalent to one of the radii of the ellipsoid. Sounds like a lot of words, but consider the auxiliary sphere having a radius of a, which is the length of our semi-minor axis. If I can draw it, so that would be a sphere that touches the ellipsoid on the equator, right? The reduced latitude would be if we were to extend a line. What color shall I use? Magenta again. A perpendicular line down to the xy plane. So that's a perpendicular line. And then if we were to extend that line up to the auxiliary sphere, we would have a point Q prime. Again, really non-intuitive, because you would expect it to be here, right? If we were to extend the radius, but no, that's not the way it works. So the reduced latitude is if we were to extend from the xy plane up to the auxiliary sphere, and then draw a line from the center of the ellipsoid up to that point, we'll call Q prime. Then this angle between the xy axis and that line we just drew is called beta, or reduced latitude. And it's defined that way because there are some calculations in which we need to consider or use the reduced latitude instead of the other latitudes we've talked about. And I will also point out that since the center of the ellipsoid is also the center of our auxiliary sphere, that makes sense, right? Think about it. Since they have the same center, but this is a sphere, then that line running, that radius running to the reduced latitude is going to be the same for any point on the sphere, and it's going to be perpendicular to the sphere, or perpendicular to the plane that's perpendicular to the sphere, or that's tangent to the sphere. And so that is reduced latitude. Not a lot of heavy material in this lecture. Get a little bit of a break because the last few have been kind of theoretically heavy. Anyway, that kind of wraps up our ellipsoid geometry. And so now we're going to start using those geometrical components to work with the LGH coordinate system. That'll be the next upcoming lectures. And we'll spend quite a bit of time on it. It's fairly detailed. So anyway, try to be patient, wait with bated breath until we can cover that. So with that, I say again, have a great rest of your day. And the rest of your week or weekend, depending on when you view this, and I will see you again soon.